Today we're going to be looking at section 5.4 in your book, Min-Max Situations. The goals of this presentation is to develop a mathematical model, analysis of a function to be used to model the situation, identification of critical points and endpoints, identification of solution, and interpretation of the solution. This is a strategy that I will be modeling across the next 3 problems. First, you want to understand the problem, read the problem carefully. You want to circle, underline, highlight any information that might be important. You want to develop a mathematical model of the problem. You want to sketch the function to see if your model is valid for the situation at hand. Identify critical points and endpoints. Solve the mathematical model using calculus, and then interpret the solution. First example I want to look at is finding 2 numbers whose sum is 10 and whose product is as large as possible. So we're maximizing product here. Let's start by defining variables. X be the first number. The second number has to be 10 minus x. And here's a reasoning. As an example, say the first number is 7. If the sum of the numbers is 10, the second number has to be 3. And 3 is computed by taking the difference of 10 and 7. So if the first number is x, the second number has to be 10 minus x because of this reason. Using these 2 variables, x as my first number and 10 minus x as my second number, I create a new function called f of x as the product of these 2 numbers, x times 10 minus x. This represents the function that we would like to maximize. Here is a graphical representation of this curve. As you can see, it has a peak somewhere between 4 and 6, and we're going to use calculus to find that peak. To maximize the function, we're going to compute critical values and apply the second derivative test. Before I take the derivative, I'm going to rewrite this function by distributing the x. X times 10 is 10x. X times x is x squared. I take the derivative, which yields 10 minus 2x, and I take the second derivative so that I can use the second derivative test. Critical value is x equals 5, and we can find that by setting 10 minus 2x equal to 0. Since the second derivative is always less than 0, is always negative, any critical numbers we find have to be maximums. So x equals 5 is a maximum value. Recalling that x is the first number, the second number is 10 minus x, or in this case 10 minus 5, so the second number is also 5. 5 plus 5 is 10, and 5 times 5 is 25. This number maximizes the product. Second example. An open top box is to be made by cutting congruent squares of side length x from the corners of a 20 by 25 inch sheet of tin and bending up the sides as shown. How large should the squares be to make the box hold as much as possible? What is the resulting volume? For this example, a diagram is provided. If a diagram is not provided for one of the examples, you should try and make one. For this example, I'm going to look at the right-hand side. We see that that side has a measurement of 20 inches. We are cutting 2 sections off. Each of those sections are of size x. For the bottom section, that section is 25 inches long, and again we are cutting sections of x off, 2 of those sections. The length is going to be 20 minus 2x. It's going to be the region that survives after cutting off those two squares of size x. Similarly, the width will be 25 minus 2x. The height of the box will be x. We're interested in the volume. The volume of the box is going to be length times width times height. In this case, our volume function is x times 20 minus 2x times 25 minus 2x. Does this function have any domain restrictions? In other words, are there certain values of x that will not work? First of all, x cannot be negative. Remember that x is the size of the squares that you're going to cut. So if x is negative, you're not cutting any triangles. So that's the left endpoint. The maximum endpoint of 10 comes into play from the second term of the volume equation, the 20 minus 2x. If x was greater than 10, that length would be negative. So the restrictions, the domain restrictions, are that x has to be between 0 and 10. Using these domain restrictions yields this sketch for v of x. Note that the curve only goes between 0 and 10. It does have a maximum. Rough estimate, between 3 and 5 is the value of x. The volume is around 800. To maximize the volume, we use calculus. First, we're going to rewrite the volume function. To get 4x cubed minus 90x squared plus 500x, all you have to do is expand the three terms above. Multiply two of them first, and then multiply in the third to the first product. Using this version of the volume function, we take the first derivative and the second derivative. Since we want to maximize, we are looking for critical points. So that's our next task. Recall that critical values are found by setting the derivative equal to 0. For this example, I used the calculator to compute those values. So you can punch it into y equals to y1 as 12x squared minus 180x plus 500, and then use either the zeros, or you can use the math menu, the solver. You can use a quadratic program, whatever method you would like to use to find these zeros. Critical values turn out to be 3.6811 and 11.3188. Recalling our domain restrictions that only values between 0 and 10 are allowed, we discard the second critical value of 11.3188. Using the second derivative test, I plug in 3.6811 into my second derivative. The result is negative 91. Since this is a negative number, we know that the critical value, 3.6811, represents a maximum. Plugging in this critical value, C1, into my volume function yields a maximum volume of 820.53 cubic inches. The last example I would like to look at is a fencing problem. Suppose that you have 100 meters of fencing to create an enclosed area for your horse. One of the sides will be the side of a barn as shown below. Question is, what dimensions maximize the enclosed area? We have two variables of interest. length and width. Because the enclosed area is rectangular, the area formula is length times width. Next, I want to use that 100 meters. So if we look at the diagram, 100 meters are going to be used up, the fencing will be used up by 2 pieces of length and 1 piece of width. Notice we were not going to place fencing up against the barn, so only 1 W and 2 lengths. That's where the equation 100 equals 2 lengths plus W comes from. This equation is equivalent to the expression width is 100 minus 2L by subtracting 2L to both sides. Plugging in W equals 100 minus 2L into the area equation leads to L times 100 minus 2L. This is the function we want to maximize. Next, we ask ourselves, are there any domain restrictions? As before, the length cannot be negative, so there is a minimum length of 0. Maximum length here is 50. Anything greater than 50, and you don't have enough fencing. Next, we look at the graphical representation of the curve. It is a parabola. Once again, the curve goes from lengths of 0 all the way up to 50. Maximum appears to happen somewhere in the 20s with a maximum area of about 1200. I'm going to use calculus to find the exact solution. Before I take the derivative, I rewrite the area formula as 100L minus 2L squared. The first derivative is 100 minus 4L. The second derivative is negative 4. In the 3 examples, I've been taking the second derivative to take advantage of the second derivative test. Next task is to calculate a critical value. To do that, I set the first derivative equal to 0. That means 100 minus 4L equals 0. You can easily confirm that the critical value occurs at a length of 25. To compute maximum area, I substitute my length of 25 meters into the area formula. This yields a maximum area of 1,250 square meters. To find the dimensions, I simply plug 25 into 100 minus 2L. That leaves a width of 50. As a summary, here is a suggested methodology to tackle these problems. It will be difficult, but with persistence, you should find that you can tackle these problems as well. Thank you for listening.